Hello and welcome back to Total Organic Chemistry. This video will be hopefully more interesting and a little bit more fun because this time we're going to be looking at an actual reaction and the mechanism that describes how that reaction occurs. So what I want to focus on is something called radical halogenation. So halogenation, adding some sort of halogen to our alkane, and radical, it's going to follow a radical process, so with single unpaired electrons. So the reaction we're going to take a look at for this video is if we take methane, CH4, and we're going to add some chlorine, Cl2 in there, and we also need either some light, so H nu is what a lot of times you'll see to represent light. In this case we're going to be using ultraviolet light, or we could also use heat, and we represent that with capital delta. And this is going to form CH3Cl, so we have removed one of those hydrogens and replaced it with a chlorine atom, and we're also going to end up with hydrochloric acid, or HCl, as a byproduct. And a lot of these radical halogenations are exothermic, but they need a catalyst to begin. And what is our catalyst going to be? Well, that is, again, the ultraviolet light or the heat. And that's going to help us start up the reaction. So, we have 3 steps to look at. First step is initiation. So again, starting up the reaction. And that's going to be where we start with our Cl2 molecule. And either our ultraviolet light or the heat is going to break this bond homolytically. So remember from my previous video, homolytic cleavage is going to break it into 2 radicals. We're going to end up with 2 chlorine radicals. And this step is rare. So only a small percentage of the chlorine molecules are going to actually be broken into chlorine radicals by either light or heat. But we only need a small amount of them to go through with the rest of the reaction. We also have propagation. And there's a couple different steps we can do for propagation. That's going to be propagating the radical. So we could possibly have maybe a Cl radical here, and a molecule of methane, and I'm just going to abbreviate CH3 and then take a look at only one of the CH bonds here. And we could have this CH bond being broken, again homolytically, because we're dealing with radicals. And that radical chlorine will form a bond with the hydrogen. So that's going to make a CH3 radical. So remember, we've taken one of the electrons from the bond to make that radical, plus our HCl. And another step we could have is maybe the methyl radical that we formed just now, attacking another molecule of chlorine, so this time the entire molecule, not the radical, and the same sort of electron movement happening here. I'm using single-headed arrows again to show the movement of single electrons, not electron pairs. And this is going to form our product, CH3Cl. plus another chlorine radical. So you can see that in each of these propagation steps, we have started with one radical and ended also with a different radical. So that's what this means by propagation. It's a chain reaction, and it's propagating that radical. And those steps will be the most common. Finally, we have termination. And as you can imagine, that means we're going to end the reaction. So we have a few different things that could happen. Maybe two chlorine radicals come together to form a bond, to reform our Cl2 molecule. We could have a methyl radical and a chlorine radical to come together and form our product, CH3Cl. Again, let me draw the lone pairs here so I don't confuse anyone. And then you could even think about having maybe two methyl radicals coming together to form ethane. So ethane is our 2-carbon alkane, CH3CH3. And all of these are rare because, like I said, we'll only have a small amount of radicals floating around at any given time because radicals are very reactive and they're not going to last for a very long time. So the probability of having two radicals come together, like here, in any of these termination steps, the probability of having two radicals close enough to react is going to be very low. So these steps do occur, but it will be much less common than, for example, the propagation steps. And with the same process, we could conceivably make other derivatives of methane as well. So maybe if we add a lot more chlorine and keep the reaction going for longer, we could add maybe 2 chlorines, 3 chlorines, so trichloromethane is also known as chloroform, or even chlorinate all of the positions to make CCl4. And those reactions can always occur as long as there's a hydrogen to pull off. You can always add another chlorine. So the next thing I want to talk about for the second half of this video is the relative reactivities of different halogens. Because we've been working with chlorine lately, but there's no reason why we couldn't use bromine or fluorine or iodine in any of these reactions. But it turns out that the fluorine radical is the most reactive. And it just goes straight down the group. All the way until iodine, which is the least reactive. And this has to do with the strength of whatever bond, so whatever halogen you have, its bond to hydrogen. So the strength of the HX bond is what determines these reactivities. Again, where X can be any of our halogens. So what we can do is draw this energy diagram that we've drawn before, with energy on the y-axis and the reaction coordinate on the x-axis. Remember, our reaction coordinate is just the extent of the reaction, how far it's gone to products. And we can take a look at, for example, the reaction between methane and fluorine, maybe catalyzed by ultraviolet light to form fluoromethane. And for this reaction, it's going to look a little bit like this. Where we start with our reactants here and our products at the end. And this hump is, remember, going to be our transition state. And the transition state, like I've talked about before, is going to be some ill-defined species with partially formed or partially broken bonds. And for this reaction, it's going to maybe look a little like this. So we have our CH3 group, and then the partially broken bond to hydrogen. I'm going to draw that dotted to show that it's not a full bond. And then the partially forming bond to fluorine. Maybe this is during the propagation step, where the fluorine radical is taking off the hydrogen from the methane. And to denote that it's a transition state, a lot of times you might see brackets around it and then this double dagger. That just shows that it's a transition state with, again, partially formed or partially broken bonds. So why have I drawn the bonds the certain length that they are here? Well, like I said, the reactivities of these halogens have to do with the strength of the HF or HCl or whatever bond strength. So the strength of that bond is going to be what we're looking at. And you can imagine, because the HF bond is relatively strong, stronger than all the other halogens, it's going to be a lot easier for the fluorine to pull off that hydrogen from the carbon. So, because it's easier for the fluorine to pull off the hydrogen, because it has that stronger bond to hydrogen, the CH bond that's being broken here is going to be shorter. In the process, when that hydrogen is coming off, the CH partially broken bond is going to be a lot shorter than the HF partially formed bond. Because again, hydrogen really likes to be with fluorine, so it doesn't take much for the hydrogen to come off of the carbon. However, if we draw another diagram the same way, except now we look at the reaction between methane and maybe iodine on the other side of the spectrum to form iodomethane or methyl iodide. The reaction maybe looks a little bit like this. Where now our transition state is over here, and I can draw the same sort of diagram for the bonds. Here. And now you can see that the length of the bonds is flipped. So now we have a very long CH bond that's being broken and a short HI bond that's forming. And that is for the same reason as the other one. The HI bond is very weak because iodine is so large and it's not very electronegative. So that HI bond is weak, So hydrogen needs to be a lot farther from the carbon in order to feel maybe the pull from the iodine atom. And you might also notice that what I've drawn here is that in the first reaction with fluorine, this transition state is very early. So this transition state is very close to the reactants, and it happens almost right away. Whereas with iodine, the transition state is very far along, and it happens almost right before we get to the products. And furthermore, the reaction with iodine is endothermic, and the reaction with fluorine is exothermic. So we're going down in energy for the exothermic reaction and up in energy for the endothermic reaction. And this relationship is what we call the Hammond postulate. So Hammond postulate. And it's going to be important for telling us how different halogens react in the radical halogenation processes, but also in other reactions as well. So what this says is that late transition states, such as the one we've drawn for iodine, are very characteristic of reactions that are slow and endothermic. Whereas the opposite is true. So very early transition states, like what we've seen for fluorine, are going to be characteristic of extremely fast and very exothermic processes. So what that means for us is that actually bromine and chlorine so they're in between the fluorine and the iodine, right? So they're actually going to be the most useful. And they'll be what we use in the future if we ever need to halogenate something with this mechanism, with this radical mechanism. So bromine and chlorine are that sweet spot. They're not too reactive, but they're also reactive enough to get the job done. Because this reaction with fluorine is so exothermic and so fast that it could actually become dangerous, produce so much heat and kind of run away. Whereas the reaction with iodine is so slow and so endothermic that nothing really happens. So it's very difficult to get iodine to actually do anything. So if you need to add iodine or fluorine to a molecule, it will probably be more useful and a lot safer to use a different method. So that's all I want to talk about in terms of this first half of radical halogenation. In the next video, I will do a little bit more discussion on halogenating different alkanes, so not just methane, but maybe alkanes with more carbons. Thank you again for watching Total Organic Chemistry. Please be sure to like and subscribe, and as well check out my Patreon page that I will link in the description.